And now the last bit. When we talk about, and I don't know yet if we're going to have any problems on this piece, but when we talk about collisions of extended bodies, like collisions with the tennis racket and things like that, it involves both linear and rotational motion. So both kinds of momentum come into play, both kinds of energy come into play. These are more sophisticated and more difficult collisions. Of course, they're closer to reality than just one or the other, because rarely is motion just simply linear or simply rotational. Another thing to think about, and we're going to talk about briefly, and again, if we were in lab, I could show you, and maybe Dr. Weber and I will get together and we'll film this for you guys. It would be pretty good to have for both her class and mine. You got to remember the rotational, the angular momentum vector, right? And angular momentum, just like momentum, is a vector. L is I omega. So if I've got a wheel rotating, its velocity vector by the right-hand rule, it's rotating, rotating like this, is towards you, or in this view, this direction. Its velocity vector is that way. And and if you're doing it with a wheel, and what we do is we spin a wheel and hang it up by one end. If you do it with a wheel, so that the wheel wants to rotate, right? I've got the wheel suspended by a rope on one end of the axle, so that it would, if it weren't spinning, it would just fall straight down like that, but it's spinning. And so now you've got an angular momentum vector this way, and a torque. The torque is which way? The torque then wants it, all right, here's the angular momentum. The vector, the torque wants it to spin this way. So the torque is back towards me, right? Angular momentum is this way. Torque is this way, all right? And torque, if you remember, right, F equals delta P over delta T. Well, the torque is back towards me. The angular momentum is this way. The torque is this way. What happens with the wheel? It doesn't fall over. What does it do? It twists this direction, right? It precesses. That's what we call it. It precesses. And so instead of falling over, it begins to twist a little bit. Now, when you're on a bicycle and you're going along, all right, and you try and move the wheel, you can feel the fact that the angular momentum doesn't want to change, and it actually takes a good bit of torque to get it to change. Or if you've ever been operating a chainsaw and really had it revved up and made the mistake of moving too fast, you can pull the chain off the guide, off the bar, all right? So there are a lot of instances where this comes into play. It's what helps us keep a bicycle up. And it's also what will create this effect where if I've got a tire spinning really fast and I'm holding it up by one side, instead of falling over, it simply begins to rotate around as the torque changes the angular momentum. Where do we see this in life in a different way? Well, it turns out over 22,000 years, the Earth does this. It's 26,000 years, pardon me. It slowly spins around so that if you were to look at Polaris, which Polaris is, from my view, right there, all right? Polaris, right there, not that it makes any difference where you're watching, but if you're on campus and you're coming out of the Union, you're facing out of the Union, Polaris is right there. And Polaris is right there, whether it's day or night, it doesn't matter. Polaris is right there. Polaris sits over our North Pole almost. Well, over this 26,000 years, Polaris actually makes a small circle in the sky. Just right now it happens to be over our North Pole. But our North Pole slowly rotates. You may have seen this when people talk about some of the pyramids because at the time some of the pyramids were built, there was a different star over the North Pole. And some of the pyramids were built looking at that star in the sky at that time. The other impact of this is if you're big into astrology, which is just a fun way of playing around with your birth date in the sky, but if you were big into astrology, the constellations are no longer where they were in the year when the Greeks were there, or when the Greeks created their stories around the stars, because the precession of the Earth changes over 26,000 years. The precession of the Earth slowly changes. So in 13,000 years, right now it's winter here in Cleveland, Mississippi. In 13,000 years, this will be summer. It'll still be December, right? It'll still be December. Well, sorry, it's not December. It's January. It'll still be January. It'll still be January, but it'll be summer. And then 13,000 years later, it'll be back to winter. As this precession slowly takes place, the seasons slowly move over 26,000 years. All right, that's it for all of our talk about momentum and and rotational motion. Good luck with all the problems, and I'll talk to you soon in class.